In this lesson, we're going to look at the properties of the normal distribution. So we saw in an earlier lesson, we graphed data, we were asked to describe the shape, among other aspects of the graph. So one shape that we saw was something called the bell shape. These were distributions that were unimodal and roughly symmetric. So if it has not slipped out in an earlier lesson, this bell-shaped curve is called the normal curve. So to quote George Box, all models are wrong, but some are useful. This pattern arrives quite frequently in just a myriad of statistical application and is very, very useful. So remember that no data will ever be perfectly normal. So the normal curve is always just an approximation that's close enough to use to approximate calculations. So notice that we sometimes smooth out the curve. We discussed earlier, we often need to describe the general pattern of the data. For example, skewed left, skewed right, or normal. So data being normally distributed, it occurs quite often. For example, I simulated rolling 2 dice and graphed the sum in a histogram. So notice that it is unimodal at about 7 and is roughly symmetric with the tails sort of sloping down from the peak. The normal curve I've superimposed over the histogram and models the situation fairly well. So notice that if I wanted to compute the exact probability that I get a sum, let's say less than 6, I would simply add up the total sums that are less than 6 and divide by 1,000 to get 0.281. So this is represented by the pink shading on the histogram shown. So if I want to use the theoretical normal model, what I'm doing here is I'm trying to find the area that's shaded underneath the normal curve that's less than 6. I get 0.331. So this smoothed out curve, sometimes called a density curve, models a continuous distribution, so versus the discrete distribution of the histogram. So we're going to discuss how we arrived at this later in this module. Recall that for discrete distributions, the sum of the probabilities was 1, and each probability was between 0 and 1. Similarly, for the continuous distribution, the total area under the curve is 1. And every point on the curve must have a vertical height greater than or equal to 1. So here's what the formula actually looks like for the normal curve. Okay, so the normal density function looks a little complicated, but don't freak out. You don't really have to memorize this for the course. We're going to be using tables or most likely technology, like the TI-84 calculator, to make our computations. I do want you to see, though, that the curve is defined by 2 parameters, mu and sigma. Mu being the mean, and sigma the standard deviation. So again, here's the curve, and I've labeled mu here for you. Note that the mean is located in the center of the normal curve, always. Sigma is this distance here. Recall that sigma, the standard deviation, dictates the spread. So one standard deviation above the mean would be written as mu plus sigma like this. Most likely, though, you're going to have numbers here to compute. We're going to see that very shortly. Let's take a quick look at this simulation. As we move the slider for the mean to the right, the entire curve just shifts to the right. The shape of the curve is not affected. Now, if we adjust sigma, the standard deviation, we can see that as it gets larger, the curve begins to flatten out. And as it gets smaller, it is relatively taller. So this app or similar app should be available for you to play with on a subsequent tab or below this lesson. So a quick note on notation. So the notation in parentheses mu comma sigma in parentheses or x in a little squiggly in parentheses mu comma sigma in parentheses. This is the abbreviation for the normal model with a mean of mu and standard deviation of sigma. So just remember that when we are working these problems and asked to work these problems, this notation may appear. We're next going to look at the standard normal distribution and then look at some applications of the normal distribution.